In this video, I'm going to talk about the history of backpropagation. I'll start with where it came from in the 70s and 80s, and then I'll talk a bit about why it failed in the 90s. That is, why serious machine learning researchers abandoned it. There was a popular view of why this happened, and we can now see that that popular view was largely wrong. The real reasons it was abandoned were because computers were too slow and datasets were too small. I'll conclude by showing you a historical document that was a bet made between two machine learning researchers in 1995. It's interesting to see what people back then believed and how wrong they were. Backpropagation was invented independently several times in the 70s and 80s. It started in the late 60s with control theorists called Bryson and Ho, who invented a linear version of backpropagation. Paul Werbus went to their lectures and realized it could be made non-linear, and in his thesis in 1974 he published what's probably the first proper version of backpropagation. Rumelhart and Williams and I invented it in 1981 without knowing about Paul Werbus's work, but we tried it out and it didn't work very well for the first thing we tried it for, and so we abandoned it. David Parker invented it in 1985, and so did Yann LeCun. Also in 1985, I went back and tried again the thing that Rumelhart, Williams and I had abandoned, and discovered it worked pretty well. And in 1986 we produced a paper with a really convincing example of what it could do. It was clear that backpropagation had a lot of promise for learning multiple layers of nonlinear feature detectors. But it didn't really live up to its promise, and by the late 1990s, most of the serious researchers in machine learning had given up on backpropagation. For example, in David Mackay's textbook, there's very little mention of it. It was still widely used by psychologists for making psychological models, and it was also quite widely used in practical applications, such as credit card fraud detection. But in machine learning, people thought it had been supplanted by support vector machines. The popular explanation of what happened to backpropagation in the late 90s was that it couldn't make use of multiple layers of nonlinear features. This wasn't true in convolutional nets, which were the exception, but in general people couldn't get feed-forward neural networks trained with backpropagation to do impressive things if they had multiple hidden layers, except for some toy examples. It also did not work well in recurrent networks or in deep autoencoders, which we'll cover in a later lecture. And recurrent networks were perhaps the place where it was most exciting, and so it was there that it was most disappointing that people couldn't make it work well. Support vector machines, by contrast, worked well. They didn't require as much expertise to make them work. They produced repeatable results, and they had a much better theory. And they had much fancier theory. So that was the popular explanation of what went wrong with backpropagation. With a more historical perspective, we can see why it really failed. The computers were thousands of times too slow, and the labelled datasets were hundreds of times too small for the regime in which backpropagation would really shine. Also, the deep networks, as well as being too small, were not sensibly initialized, and so backpropagating through deep networks didn't work well because the gradients tended to die because the initial weights were typically too small. These issues prevented backpropagation from being successful for tasks like vision and speech, where it would eventually be a big win. So we need to distinguish between different kinds of machine learning tasks. There's ones that are more typical of the kinds of things people study in statistics, and ones that are more typical of the kinds of things people study in artificial intelligence. So at the statistics end of the spectrum, you typically have low-dimensional data. A statistician thinks of 100 dimensions as high-dimensional data. At the artificial intelligence end of the spectrum, things like images or coefficients representing speech typically have many more than 100 dimensions. At the statistics end of the spectrum, there's usually a lot of noise in the data, whereas in the AI end of the spectrum, noise isn't the real problem. For statistics, there's often not that much structure in the data, and what structure there is can be captured by a fairly simple model. At the AI end of the spectrum, there's typically a huge amount of structure in the data. So if you take a set of images, it's highly structured data, but the structure is too complicated to be captured by a simple model. So in statistics, the main problem is separating true structure from noise, not thinking that noise is really structure. This can be done by a Bayesian neural net pretty well, but for typical non-Bayesian neural nets, it's not the kind of problem they're good at. And so for problems like that, it makes sense to try a support vector machine, or a method called a Gaussian process if you're doing regression, which I'll talk about briefly later. At the artificial intelligence end of the spectrum, the main problem is to find a way of representing all this complicated structure so that it can be learned. The obvious thing to do is to try to hand design appropriate representations, but actually it's easier to let backpropagation figure out what representations to use by giving it multiple layers and using a lot of computation power to let it decide what the representation should be. I now want to talk very briefly about support vector machines. I'm not going to explain how they work, but I am going to say what I think their limitations are. So there's several ways in which you can view a support vector machine, and I'm going to give you two different views of them. According to the first view, support vector machines are just a reincarnation of perceptrons with a clever trick called the kernel trick. So the idea is that you take the inputs, you expand the raw input into a very large layer of non-linear but also non-adaptive features. So that's just like perceptrons, where you have this big layer of features that doesn't learn. And then you only have to learn one layer of adaptive weights, the weights from the features to the decision unit. And support vector machines have a very clever way of avoiding overfitting when they learn those weights. They look for what's called a maximum margin hyperplane in a high-dimensional space, and they can do that much more efficiently than you might have thought possible, and that's why they work well. The second view also views support vector machines as a clever reincarnation of perceptrons, but it has a completely different notion of what kinds of features they're using. So according to the second view, each input vector in the training set is used to define one feature. I'll spell it differently to indicate it's a completely different kind of feature from the first kind. Each of these features gives a scalar value which involves doing a global match between a test input and that particular training input. So roughly speaking, it's how similar the test input is to a particular training case. Then there's a clever way of simultaneously finding how to weight those features so as to make the right decision, and also doing feature selection, that is, deciding which of those features not to use. So although these views sound extremely different from one another, they're just two alternative ways of looking at the same thing, a support vector machine, and in both cases it's using non-adaptive features and then one layer of adaptive weights. And there's limits to what you can do that way. You can't learn multiple layers of representation with a support vector machine. This is a historical document from 1995. It was given to me by Yann Lequin, and it's a bet between Larry Jackal, who headed the Adaptive Systems Research Group at Bell Labs, and Vladimir Vapnik, who is the leading proponent of support vector machines. Larry Jackal bet that by 2000 people would understand why big neural nets trained with backpropagation worked well on large data sets. That is, they would understand it theoretically in terms of conditions and bounds. Vapnik bet that they wouldn't, but he made a side bet that if he was the one to figure it out, he would win anyway. Vapnik in turn bet that by 2005 nobody would be using big neural nets like that trained with backpropagation. It turns out that they were both wrong. The limitation to using big neural nets with backpropagation was not that we didn't have a good theory, and not that they were essentially hopeless, but that we didn't have big enough computers or big enough data sets. It was a practical limitation, not a theoretical one. In this lecture, I'll introduce belief nets. One of the reasons I abandoned backpropagation in the 1990s was because it required too many labels. Back then we just didn't have datasets with sufficient numbers of labels. I was also influenced by the fact that people managed to learn with very few explicit labels. However, I didn't want to abandon the advantages of doing gradient descent learning to learn a whole bunch of weights. So the issue was there another objective function that we could do gradient descent in? The obvious place to look was generative models, where the objective function is to model the input data rather than predicting a label. This meshed nicely with a major movement in statistics and artificial intelligence called graphical models. The idea of graphical models was to combine discrete graph structures for representing how variables depended on one another with real-valued computations that inferred the probability of one variable given the observed values of other variables. Boltzmann machines were actually a very early example of a graphical model, but they were undirected graphical models. In 1992, Radford Neal pointed out that using the same kinds of units as we used in Boltzmann machines, we could make directed graphical models, which he called Sigmoid belief nets. And the issue then became, how can we learn Sigmoid belief nets? A second problem is that for deep networks, the learning time does not scale well. When there's multiple hidden layers, the learning was very slow. You might ask why this was, and we now know that one of the reasons was we did not initialize the weights in a sensible way. Yet another problem is that backpropagation can get stuck in poor local optima. These are often quite good, so backpropagation is useful, but we can now show that for deep nets, the local optima you get stuck in if you start with small random weights are typically far from optimal. There is the possibility of retreating to simpler models that allow convex optimization, but I don't think this is a good idea. Mathematicians like to do that because they can prove things, but in practice you're just running away from the complexity of real data. So one way to overcome the limits of backpropagation is by using unsupervised learning. The idea is that we want to keep the efficiency and simplicity of using a gradient method and stochastic mini-batch descent for adjusting the weights, but we're going to use that method for modelling the structure of the sensory input, not for modelling the relation between input and output. So the idea is the weights are going to be adjusted to maximise the probability that a generative model would have generated the sensory input. We already saw that in learning Boltzmann machines. And one way to think about it is, if you want to do computer vision, you should first learn to do computer graphics. To first order, computer graphics works and computer vision doesn't. The learning objective for a generative model, as we saw with Boltzmann machines, is to maximise the probability of the observed data, not to maximise the probability of labels given inputs. Then the question arises, what kind of generative model should we learn? We might learn an energy-based model like a Boltzmann machine, or we might learn a causal model made of idealized neurons, and that's what we'll look at first. Or finally, we might learn some kind of hybrid of the two, and that's where we'll end up. So before I go into causal belief nets made of neurons, I want to give a little bit of background about artificial intelligence and probability. In the 1970s and early 1980s, people in artificial intelligence were unbelievably anti-probability. When I was a graduate student, if you mentioned probability, it was a sign that you were stupid and you just hadn't got it. Computers were all about discrete symbol processing, and if you introduced any probabilities, they would just infect everything. It's hard to conceive of how much people were against probability, so here's a quote to help you. I'll read it out. Many ancient Greeks supported Socrates' opinion that deep, inexplicable thoughts came from the gods. Today's equivalent to those gods is the erratic, even probabilistic neuron. It is more likely that increased randomness of neural behaviour is the problem of the epileptic and the drunk, not the advantage of the brilliant. That was in Patrick Henry Winston's first AI textbook in the first edition, and it was the general opinion at the time. Winston was to become the leader of the MIT AI lab. Here's an alternative view. All of this will lead to theories of computation which are much less rigidly of an all-or-none nature than past and present formal logic. There are numerous indications to make us believe that this new system of formal logic will move closer to another discipline which has been little linked in the past with logic. This is thermodynamics, primarily in the form it was received from Boltzmann. That was written by John von Neumann in 1957 and was part of the unfinished manuscript he left behind for what was to be his crowning achievement, his book on the computer and the brain. I think if von Neumann had lived, the history of artificial intelligence might have been somewhat different. So probabilities eventually found their way into AI via something called graphical models, which are a marriage of graph theory and probability theory. In the 1980s, there was a lot of work on expert systems in AI that used bags of rules for tasks such as medical diagnosis or exploring for minerals. Now these were practical problems, so they had to deal with uncertainty. They couldn't just use toy examples where everything was certain. People in AI disliked probability so much that even when they were dealing with uncertainty, they didn't want to use probabilities, so they made up their own ways of dealing with uncertainty that did not involve probabilities. You can actually prove that this is a bad bet. Graphical models were introduced by Pearl, Heckermann, Luritzen, and many others, who showed that probabilities actually worked better than the ad hoc methods developed by people doing expert systems. Discrete graphs were good for representing what variable depended on what other variables. But once you had those graphs, you then needed to do real-valued computations that respected the rules of probability so that you could compute the expected values of some nodes in the graph given the observed states of other nodes. Belief nets is the name that people in graphical models give to a particular subset of graphs, which are directed acyclic graphs, and typically they use sparsely connected ones. And if those graphs are sparsely connected, they have clever inference algorithms that can compute the probabilities of unobserved nodes efficiently. But these clever algorithms are exponential in the number of nodes that influence each node, so they won't work for densely connected nets. So a belief net is a directed acyclic graph composed of stochastic variables, and here's a picture of one. In general, you might observe any of the variables. I'm going to restrict myself to nets in which you only observe the leaf nodes. So we imagine there's these unobserved hidden causes, and they may be layered, and they eventually give rise to some observed effects. Once we observe some variables, there's two problems we'd like to solve. The first is what I'll call the inference problem, and that's to infer the states of the unobserved variables. Of course, we can't infer them with certainty, so what we're after is probability distributions over unobserved variables. And if the unobserved variables are not independent of one another, given the observed variables, those probability distributions are likely to be big, cumbersome things with an exponential number of terms in. The second problem is the learning problem. That is, given a training set composed of observed vectors of states of all of the leaf nodes, how do we adjust the interactions between variables to make the network more likely to generate that training data? So adjusting the interactions will involve both deciding which node is affected by which other node, and also deciding on the strength of that effect. So let me just say a little bit about the relationship between graphical models and neural networks. The early graphical models used experts to define the graph structure and also the conditional probabilities. They would typically take a medical expert and ask him how likely is this to cause that, and then they would make a graph in which the nodes had meanings, and they typically had conditional probability tables that described how a set of values for the parents of a node would determine the distribution of values for the node. Their graphs were sparsely connected, and the initial problem they focused on was how to do correct inference. Initially they weren't interested in learning, because the knowledge came from the experts. By contrast, for neural nets, learning was always the central issue, and hand-wiring the knowledge was regarded as not cool. Although, of course, wiring in some basic properties, as in convolutional nets, was a very sensible thing to do. But basically, the knowledge in the net came from learning the training data, not from experts. Neural networks didn't aim to have interpretability or sparse connectivity to make the inference easy. Nevertheless, there are neural network versions of belief nets. So if we think about how to make generative models out of idealized neurons, there's basically two types of generative model you can make. There's energy-based models, where you connect binary stochastic neurons using symmetric connections, and then you get a Boltzmann machine. A Boltzmann machine, as we've seen, is hard to learn, but if we restrict the connectivity, then it's easy to learn a restricted Boltzmann machine. However, when we do that, we've only learned one hidden layer, and so we're giving up on a lot of the power of neural nets with multiple hidden layers in order to make learning easy. The other kind of model you can make is a causal model. That is, a directed acyclic graph composed of binary stochastic neurons. And when you do that, you get a sigmoid belief net. In 1992, Neil introduced models like this and compared them with Boltzmann machines and showed that sigmoid belief nets were slightly easier to learn. So a sigmoid belief net is just a belief net in which all of the variables are binary stochastic neurons. To generate data from this model, you take the neurons in the top layer, you determine whether they should be ones or zeros based on their biases, so you determine that stochastically, and then given the states of the neurons in the top layer, you make stochastic decisions about what the neurons in the middle layer should be doing, and then given their binary states, you make decisions about what the visible effects should be, and by doing that sequence of operations, a causal sequence from layer to layer, you would get an unbiased sample of the kinds of vectors of visible values that your neural network believes in. So in a causal model, unlike a Boltzmann machine, it's easy to generate samples.
In this video, I'll talk about why it's difficult to learn sigmoid belief nets. And then in the following two videos, I'll describe two different methods we discovered that allow us to do the learning. The good news about learning in sigmoid belief nets is that unlike Boltzmann machines, we don't need two different phases. We just need what in a Boltzmann machine would be the positive phase. That's because sigmoid belief nets are what is called locally normalized models, so we don't have to deal with a partition function or its derivatives. Another piece of good news about sigmoid belief nets is that if we could get unbiased samples from the posterior distribution over the hidden units, given a data vector, then learning would be easy. That is, we could follow the gradient specified by maximum likelihood learning in a mini-batch stochastic kind of a way. The problem is that it's hard to get unbiased samples from the posterior distribution over the hidden units. This is largely due to a phenomenon that Judea Pearl calls explaining away. And I'll explain explaining away in this video, and it's important to understand it.
Now I'm going to talk about why it's difficult to learn sigmoid belief nets. As we've seen, it's easy to generate an unbiased sample once you've done the learning. That is, once we've decided on the weights in the network, we can easily see the kinds of things the network believes in by generating samples from its model. This is done top-down, one layer at a time. It's easy because it's a causal model. However, even if we know the weights, it's hard to infer the posterior distribution over hidden causes when we observe the visible effects. The reason for this is that the number of possible patterns of hidden causes is exponential in the number of hidden nodes. It's hard even to get a sample from the posterior, which is what we need if we're going to do stochastic gradient descent. So given this difficulty in sampling from the posterior, it's hard to see how we can learn sigmoid belief nets with millions of parameters, which is what we'd like to do. Notice this is a very different regime from the one normally used with graphical models. There they have interpretable models, and they're trying to learn dozens or maybe hundreds of parameters. They're not typically trying to learn millions of parameters. Now, before I go into ways in which we can try and get samples from the posterior distribution, I just want to tell you what the learning rule is if we could get those samples. So if we can get an unbiased sample from the posterior distribution over hidden states, given the observed data, then learning is easy. So here's part of a sigmoid belief net, and we're going to suppose that for every node we have a binary value. So for node j, that binary value is sj, and that vector of binary values is a global configuration for the net, which is a sample from the posterior distribution. In order to do maximum likelihood learning, all we have to do is maximize the log probability that the inferred binary state of unit I would be generated from the inferred binary states of its parents. So the learning rule is local and simple. The probability that the parents of I would turn I on is given by a logistic function that involves the binary states of the parents. And what we need to do is make that probability be similar to the actually observed binary value of I. And although I'm not going to derive it here, the maximum likelihood learning rule for the weight wji is simply to change it in proportion to the state of j times the difference between the binary state of I and the probability that the binary states of I's parents would turn it on. So to summarize, if we have an assignment of binary states to all the hidden nodes, then it's easy to do maximum likelihood learning in our typical stochastic way, where we sample from the posterior and then we update the weights based on that sample, and we average that update over a mini batch of samples. So let's go back to the issue of why it's hard to sample from the posterior. The reason it's hard to get an unbiased sample from the posterior over the hidden nodes, given an observed data vector at the leaf nodes, is a phenomenon called explaining away. So if you look at this little sigmoid belief net here, it has two hidden causes and one observed effect. And if you look at the biases, you'll see that the observed effect of a house just jumping is very unlikely to happen unless one of those causes is true. But if one of those causes has happened, the 20 cancels the minus 20, and now the house will jump with a probability of a half. Each of the causes is itself rather unlikely, but not nearly as unlikely as a house spontaneously jumping. So if you see the house jump, one plausible explanation is that a truck hit the house. A different plausible explanation is that there was an earthquake. And each of those has a probability of about e to the minus 10, whereas the house jumping spontaneously has a probability of about e to the minus 20. However, if you assume both hidden causes, that has a probability of e to the minus 20, so that's extremely unlikely, even if the house did jump. So, assuming there was an earthquake reduces the probability that the house jumped because a truck hit it, and we get an anti-correlation between the two hidden causes when we've observed the house jumping. Notice in the model itself, in the prior for the model, these two hidden causes are quite independent. So if the house jumps, there's basically an even chance that was because of a truck or because of an earthquake. The posterior actually looks something like this. There's 4 possible patterns of hidden causes, given that the house jumped. 2 of them are extremely unlikely, namely that a truck hit the house and there was an earthquake, or that neither of those things happened. The other 2 combinations are equally probable, and you'll notice they form an exclusive OR. we have two likely patterns of causes, which are just the opposites of each other. That's explaining away. Now that we've understood explaining away, let's go back to the issue of learning a deep sigmoid belief net. So we're going to have multiple layers of hidden variables. They're going to give rise to some data in our causal model. And we want to learn those weights W between the first layer of hidden variables and the data. And let's see what it takes to learn W. First of all, the posterior distribution over the first layer of hidden variables is not going to be factorial. They're not independent in the posterior. And that's because of explaining away. So even if we just had that layer of hidden variables, once we've seen the data, they wouldn't be independent of one another. But because we have higher layers of hidden variables, they're not even independent in the prior. Those hidden variables in the layers above create a prior, and that prior will itself cause correlations between the hidden variables in the first layer. To learn W, we need to know the posterior in the first hidden layer, or at least an approximation to it. And even if we're only approximating it, we need to know all of the weights in higher layers in order to compute that prior term. In fact, it's even worse than that, because to compute that prior term, we need to integrate out all the hidden variables in higher layers. That is, we need to consider all possible patterns of activity in these higher layers and combine them all to compute the prior that the higher layers create for the first hidden layer. Computing that prior is a very complicated thing. So these three problems suggest that it's going to be extremely difficult to learn those weights W. And in particular, we're not going to be able to learn them without doing a lot of work in the higher layers to compute the prior. So now we're going to consider some methods for learning deep belief nets. The first one is the Monte Carlo method used by Radford-Neal, and that Monte Carlo method basically does all the work. That is, if we go back to the previous slide, it considers patterns of activity over all the hidden variables, and it runs a Markov chain that takes a long time to settle down, given a data vector, and once it's settled down to thermal equilibrium, you get a sample from the posterior, but it's a lot of work. So in large, deep belief nets, this method's pretty slow. In the 1990s, people developed much faster methods for learning deep belief nets, which were called variational methods. In fact, this is where variational methods came from, at least for the artificial intelligence community. The variational methods give up on getting unbiased samples from the posterior, and they content themselves with just getting approximate samples, that is, samples from some other distribution that approximates the posterior. Now, as we saw before, if we have samples from the posterior, maximum likelihood learning is simple. If we have samples from some other distribution, we could still use the maximum likelihood learning rule, but it's not clear what will happen. On the face of it, crazy things might happen if we're using the wrong distribution to get our samples. There doesn't seem to be any guarantee that things will improve. In fact, there is a guarantee that something will improve. It's not the log probability that the model would generate the data, but it is related to that. In fact, it's a lower bound on that log probability. And by pushing up the lower bound, we can usually push up the log probability.
In this video, I'll describe the first way we discovered for getting sigmoid belief nets to learn efficiently. It's called the wake-sleep algorithm, and it should not be confused with Boltzmann machines. They have two phases, a positive and a negative phase, that could plausibly be related to wake and sleep. But the wake-sleep algorithm is a very different kind of learning, mainly because it's for directed graphical models like sigmoid belief nets, rather than for undirected graphical models like Boltzmann machines. The ideas behind the wake-sleep algorithm led to a whole new area of machine learning called variational learning, which didn't take off until the late 1990s, despite early examples like the wake-sleep algorithm, and is now one of the main ways of learning complicated graphical models in machine learning. The basic idea behind these variational methods sounds crazy. The idea is that since it's hard to compute the correct posterior distribution, we'll compute some cheap approximation to it, and then we'll do maximum likelihood learning anyway. That is, we'll apply the learning rule that would be correct if we'd got a sample from the true posterior, and hope that it works even though we haven't. Now, you could reasonably expect this to be a disaster, but actually the learning comes to your rescue. So if you look at what's driving the weights during the learning, when you use an approximate posterior, there are actually two terms driving the weights. One term is driving them to get a better model of the data. That is, to make the sigmoid belief net more likely to generate the observed data in the training set. But there's another term that's added to that that's actually driving the weights towards sets of weights for which the approximate posterior you're using is a good fit to the real posterior. It does this by manipulating the real posterior to try and make it fit the approximate posterior. It's because of this effect that variational learning of these models works quite nicely. Back in the mid-90s, when we first came up with it, we thought this was an interesting new theory of how the brain might learn. That idea has been taken up since by Carl Friston, who strongly believes this is what's going on in real neural learning.
So we're now going to look in more detail at how we can use an approximation to the posterior distribution for learning. To summarize, it's hard to learn complicated models like sigmoid belief nets because it's hard to get samples from the true posterior distribution over hidden configurations when given a data vector. And it's hard even to get a sample from that posterior. That is, it's hard to get an unbiased sample. So the crazy idea is that we're going to use samples from some other distribution and hope that the learning will still work. And as we'll see, that turns out to be true for sigmoid belief nets. So the distribution that we're going to use is a distribution that ignores explaining away. We're going to assume wrongly that the posterior over hidden configurations factorizes into a product of distributions for each separate hidden unit. In other words, we're going to assume that given the data, the units in each hidden layer are independent of one another, as they are in a restricted Boltzmann machine. But in a restricted Boltzmann machine, this is correct, whereas in a sigmoid belief net, it's wrong. So let's quickly look at what a factorial distribution is. In a factorial distribution, the probability of a whole vector is just the product of the probabilities of its individual terms. So suppose we have 3 hidden units in a layer, and they have probabilities of being on of 0.3, 0.6 and 0.8. If we want to compute the probability of the hidden layer having the state 1, 0, 1, we compute that by multiplying 0.3 by 1 minus 0.6 by 0.8. So the probability of a configuration of the hidden layer is just the product of the individual probabilities. That's why it's called factorial. In general, a distribution over binary vectors of length n will have 2 to the n degrees of freedom. Actually, it's only 2 to the n minus 1, because the probabilities must add to 1. A factorial distribution, by contrast, only has n degrees of freedom. It's a much simpler beast. So now I'm going to describe the wake-sleep algorithm that makes use of the idea of using the wrong distribution. And in this algorithm, we have a neural net that has 2 different sets of weights. It's really a generative model, and so the weights shown in green for generative are the weights of the model. Those are the weights that define the probability distribution over data vectors. We've got some extra weights, the weights shown in red for recognition weights, and these are weights that are used for approximately getting the posterior distribution. That is, we're going to use these weights to get a factorial distribution at each hidden layer that approximates the posterior, but not very well. So in this algorithm, there's a wake phase. In the wake phase, you put data in at the visible layer at the bottom, and you do a forward pass through the network using the recognition weights, and at each hidden layer you make a stochastic binary decision for each hidden unit independently about whether it should be on or off. So the forward pass gets us stochastic binary states for all of the hidden units. Then, once we have those stochastic binary states, we treat that as though it was a sample from the true posterior distribution given the data, and we do maximum likelihood learning. But what we're doing maximum likelihood learning for is not the recognition weights that we just used to get the approximate sample, it's the generative weights that define our model. So you drive the system in the forward pass with the recognition weights, but you learn the generative weights. In the sleep phase, you do the opposite. You drive the system with the generative weights. That is, you start with a random vector at the top hidden layer. You generate the binary states of those hidden units from their prior, in which they're independent. And then you go down through the system, generating states for each layer at a time. And here you're using the generative model correctly. That's how the generative model says you ought to generate data. And so you can generate an unbiased sample from the model. Having used the generative weights to generate an unbiased sample, you then say, let's see if we can recover the hidden states from the data. Or let's see if we can recover the hidden states at layer H2 from the hidden states at layer H1. So you train the recognition weights to try and recover the hidden states that actually generated the states in the layer below. So it's just the opposite of the wake phase. We're now using the generative weights to drive the system, and we're learning the recognition weights. It turns out that if you start with random weights, and you alternate between wake phases and sleep phases, it learns a pretty good model. There are flaws in this algorithm. The first flaw is a rather minor one, which is the recognition weights are learning to invert the generative model. But at the beginning of learning, they're learning to invert the generative model in parts of the space where there isn't any data. Because when you generate from the model, you're generating stuff that looks very different from the real data, because the weights aren't any good. That's a waste, but it's not a big problem. The serious problem with this algorithm is that the recognition weights not only don't follow the gradient of the log probability of the data, they don't even follow the gradient of the variational bound on this probability. And because they're not following the right gradient, we get incorrect mode averaging, which I'll explain on the next slide. A final problem is that we know that the true posterior over the top hidden layer is bound to be far from independent because of explaining away effects, and yet we're forced to approximate it with a distribution that assumes independence. This independence approximation might not be so bad for intermediate hidden layers, because if we're lucky, the explaining away effects that come from below will be partially cancelled out by prior effects that come from above. You'll see that in much more detail later. Despite all these problems, Carl Friston thinks this is how the brain works. When we initially came up with the algorithm, we thought it was an interesting new theory of the brain. I currently believe that it's got too many problems to be how the brain works, and that we'll find better algorithms. So now let me explain mode averaging using the little model with the earthquake and the truck that we saw before. Suppose we run the sleep phase and we generate data from this model. Most of the time, those top two units will be off because they're very unlikely to turn on under their prior. And because they're off, the visible unit will be firmly off because of its bias of -20. Just occasionally, one time in about e to the -10, one of the two top units will turn on, and it'll be equally often the left one and the right one. When that unit turns on, there's a probability of a half that the visible unit will turn on. So if you think about the occasions on which the visible unit turns on, half those occasions have the left-hand hidden unit on, the other half of those occasions have the right-hand hidden unit on, and almost none of those occasions have neither or both units on. So now think what the learning will do for the recognition weights. Half the time we have a 1 on the visible there, the leftmost unit will be on at the top, so it will actually learn to predict that that's on with a probability of 0.5, and the same for the right unit. So the recognition units will learn to produce a factorial distribution over the hidden layer of 0.5, 0.5. Now that factorial distribution puts a quarter of its mass on the configuration 1, 1, and another quarter of its mass on the configuration 0, 0, and both of those are extremely unlikely configurations given that the visible unit was on. It would have been better just to pick one mode. That is, it would have been better for the visible unit just to vote for truck or just to vote for earthquake. That's the best recognition model you can have. That's the best recognition model you can have if you're forced to have a factorial model. So even though the hidden configurations we're dealing with are best represented as the corners of a square, I'll actually show it as if it was a one-dimensional continuous value. And the true posterior is bimodal. It's focused on 1, 0 or 0, 1. That's shown in black. The approximation we'll learn, if we use the sleep phase of the wake-sleep algorithm, is the red curve, which gives all 4 states of the hidden units equal probability. And the best solution would have been to pick one of its states and give it all the probability mass. That's the best solution because in variational learning we're manipulating the true posterior to make it fit the approximation we're using. Normally in learning we're manipulating an approximation to fit the true thing, but here it's backwards.